Hello and welcome to the video looking at epistasis. I'm going to be looking at both recessive and dominant epistasis and also looking at complementary epistasis. So we'll start off by saying what the general term of epistasis means. It's the interaction of non-linked gene loci where one masks the expression of the other. The one that is masking the other is called the epistatic allele, and the one that has been affected, one that is being masked, is the hypostatic allele. Okay. So, recessive epistasis is when the epistatic allele would be recessive, and you would need two recessive, or you need two epistatic alleles for it to affect the masking of the hypostatic allele. So I'm going to use the example of the flower colour of salvia plants. So the pure breeding pink flowered variety has the genotype capital A, lowercase b, lowercase b. Okay. And if that was crossed with a pure breeding white flower, which is lowercase a, capital B, all the first generation offspring would be purple flowers, and their genotype is capital A, lowercase a, capital B, lowercase b. They're purple. These are white. These are pink. So, the homozygous lowercase a, that is epistatic to both of the B alleles. So when there is a homozygous recessive A, then this will prevent any colour being expressed. So neither the B for purple or the B for pink can be expressed if there is homozygous recessive A, then it would be white. And when we cross these, we can see a modified ratio. It's a modification of the dihybrid ratio, and I will show you this in a Punnett Square. Okay, so if we've got all purple flowers, if we've got the pink and the white, we know the pink was capital A, little b, and then the white was A, B, like this. We know that their gametes would have been A, B, like so, and that would have all been, the first generation would have been all A, B, heterozygous, all purple. Okay. And now from this we can form the first generation gametes. So we've got the possibilities. We could have capital A, capital B. I'll put these in the diagram now actually. It might not be the best diagram. Okay, so capital A, capital B, capital A, lowercase b, lowercase a, capital B, lowercase a, lowercase b. And then we would have, again, I've done this a bit wrong, but it doesn't matter. Do it like that. So we've got another capital A, capital B, capital A, little case b, little a, big B. And then we will have little a, little b. And then if we're crossing these, we've got big A, big A, big B, big B. That is homozygous dominant. And then we know this is going to be big A, big B, little b. Big A, little a. I'll just go through these quickly and then we will have a look in a second at what these mean. You could have a go at thinking about what this would be before I go and explain it. Right, so the reason this ratio would be modified is because we need to remember that if we have two recessive A's in a homozygous state, then the colour cannot be expressed. So here we've got two dominant B's, so we know that it will be what colour? Pink. I forgot what the thing is now. So big B would be for purple. This one's pink. So this would be purple. This would be purple because it's heterozygous. This would be purple. This would be purple. Purple, 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 purple. And now here, it would be purple, but we've actually got the two recessive A's. So this will be white because we've got, this is masking the expression of that. This is the same here, going to be white. Here, this will be purple. Here, we've got two lowercase b's, then we've got dominant A, so that means that we can express it, it's going to be pink. Here, we've got the two A's, it's going to be white again. Here, it would be pink, but it's not, it's going to be white, okay? Oh, this is a lowercase b, sorry, I've done that wrong, then that would be b. So this here, that would be pink too. Anyway, so we see that this would be purple. We see that we've got 1 pink, 2 pink, 3 pink. We've got 3 pink. We've got 1, 2, 3, 4 white, and 1, 2, 3, 4, 5, 6, 7, 8, 9 purple. And then, so this is how we create the 9 to 3 to 4 ratio. And now in a normal Mendelian one of a dihybrid cross, it would be 9 to 3 to 3 to 1. But we can just see how this is modified slightly. We've got 9 to 3 to 4. So that is recessive epistasis. But we're going to have a look at dominant epistasis as well. I'll just clean the board. We can go through that. Okay. So, dominant epistasis is the same kind of idea. We just need the epistatic allele is going to be dominant. So, we're only going to need one epistatic allele to mask the expression of the hypostatic allele. So, we're looking at an example then. For example, in the chicken, in fact, we'll just stay with the pink colours. So let's just say if hypothetically it was dominant, then we would only need one like that. This would stop the expression of purple because we'd got this here. It wouldn't matter that this wasn't. There'd be no colour and it'd be white. Okay, there's lots of different examples, but I'm just gonna whiz past that. There is a way that they could express it in exams. I'm just going to mention quickly because I don't want to get confused if this comes up. So if there was a genotype, for example, if we're looking at combs of chicken, so whether it be a walnut comb, rose comb, pea comb, single comb, etc. So for a walnut comb, then the genotype is represented like, oh sorry, that's wrong. P, capital P dash, capital R dash, and what that, can you see that there? What that means is that it wouldn't matter what came after that capital P or after the R, whatever it was, it would still produce a walnut comb. So it could be P, capital P, lowercase p, capital R, lowercase r, or it could be capital and a capital. It doesn't matter which way around it is. So for rose comb, it is lowercase p, capital R dash. So it could be another capital R or it could be a lowercase r, and that would still produce a P comb. Okay, so that's that. And then the last part about epistasis then is, because what we've covered so far is looking at antagonistic epistasis, whereas the presence of one of an epistatic allele masks the expression of the hypostatic allele. But for complementary epistasis, it's where the genes work together to produce the final phenotype. So for the sweet peas and for the white flowers, we had sweet pea. If this produced white flowers, and we crossed this with capital T, then all the offspring would be purple. And a possible explanation is they look at complementary epistasis is looking at this as a series of reactions. So we could have a precursor, and then we'd have like intermediate to the final. So in fact, I'm going to use a simpler example. For coat colour in mice, it can be white, black, or agouti, which is like grey. So what would happen is this precursor, like the substance, you would then need the gene a capital C, or we can only go from this to this if that capital C allele is present, okay, or lowercase c, or whatever the combination might be. If it has one dominant allele, it needs at least one dominant allele to go to the black pigment, okay. And then we can say that for it to go from this to the agouti, we need at least one dominant A allele. So then we must have at least one dominant C to express the colour, and at least one dominant A for the grey at the final pigment here. So we can see it as more of a series of reactions rather than it being masked by another thing, okay. So that is that for epistasis. Thank you for watching.